Hello. So this question was asked for Assistant Professor Mechanical Engineering exam in 2016. So the printer's ink is an example of choices given are Newtonian fluid, ideal fluid, Thixotropic fluid and plastic fluid. Printer's ink. Answer is Thixotropic fluid. So let's see the various options. So what are Newtonian fluids? Newtonian fluids. So basically Newtonian fluids are fluids for which shear stress is directly proportional to rate of deformation. Shear stress is proportional to rate of deformation. This du by dy is known as rate of deformation, or also known as velocity gradient, du by dy, or velocity gradient. So this tau is called shear stress, or we can remove the proportionality constant and we can write it as tau equal to mu du by dy. Here mu is called coefficient of viscosity. Mu is the coefficient of viscosity. Also known as dynamic viscosity. Dynamic viscosity. The unit of mu is Pascal second. Mu has the unit of Pascal second, where Pascal is the unit of pressure. Or we can also write that pressure is equal to force by area, or unit of pressure is Newton per meter square into second. So this is the unit of dynamic viscosity. So all fluids in reality has mu greater than 0. So all fluids in reality has mu greater than 0. So some examples of Newtonian fluids are water, air, oil, etc. are examples of Newtonian fluids. So another unit of viscosity is of viscosity is also called poise. Here 1 Pascal second is equal to 10 poise. 1 Pascal second is equal to 10 poise. So let's draw a curve between shear stress and rate of deformation. So let's draw a curve between shear stress and rate of deformation. Here y-axis let it be shear stress and x-axis let it be deformation, or du by dy. So we know that shear stress is directly proportional to rate of deformation and velocity gradient. So this will be linear variation. So let this be for water. So oils viscosity will be higher. So we have for oils, this will be the line for oil, and for air the value, again air is also a Newtonian fluid, so the value will be less than that of water. So here slope of this denotes the viscosity. Viscosity is given by slope. So from Newton's law of viscosity we know that shear stress is equal to mu du by dy, or tau by u is equal to du by dy, or shear stress tau is equal to force by area into mu is equal to du by dy. Or from this equation we will get tau equal to, or mu is equal to tau by du by dy. So basically here tau is denoted in the y-axis and du by dy is denoted in the x-axis. So mu is given as the slope of this curve. For non-Newtonian fluids, the relationship is not linear. So let's again plot the shear stress and deformation curve. So here let it be tau, and y-axis the x-axis let's mark it as du by dy. Now this denotes the Newtonian fluid. So for non-Newtonian fluid, the shear stress relationship between shear stress and deformation is non-linear. So we can draw, it's not a straight line, and draw it here. So this curve is generally denotes dilatant fluid, and the top curve basically denotes pseudoplastic. So these dilatant fluids are also known as shear thickening fluid. So dilatant fluids are basically fluids, or shear thickening fluids are fluids for which viscosity increases with the rate of deformation. Here viscosity increases with rate of deformation. So you can see that the slope here is less. So as we move ahead, as the rate of deformation increases, the viscosity increases. Hence these types of fluids are known as shear thickening fluid, or the viscosity basically increases with the rate of deformation. Examples of shear thickening fluids are solutions with suspended starch, or butter, quicksand, sugar in water, aqueous suspension of rice starch, etc. So the fluids which exhibit the opposite behavior, or that is viscosity decreases with rate of deformation. So those fluids are known as pseudoplastic fluids. Examples are paint, gelatin, paper pulp, rubber solution, etc. So there is another class of fluids which are known as Bingham plastics. So Bingham plastics can resist finite shear stress, and they behave as a solid. They can resist finite amount of shear stress, and thus they behave as a solid. But it deforms continuously, deforms continuously when the stress exceeds the yield stress. When stress exceeds the yield stress. So we can plot it as, so it can resist a finite amount of shear stress. So there is basically a finite amount of shear stress. So x is tau, this is du by dy, but later on it deforms continuously. Such fluids are known as Bingham plastics. Example is toothpaste. Now there are certain time-dependent fluids. So if you plot a graph between viscosity and stress over time, plot a graph between viscosity and stress over time. For some fluids, the time dependent shear exhibits shear thinning property, or viscosity decreases over time, or time dependent shear thinning property is observed. So such fluids are known as thixotropic fluids. Thixotropic fluids, or time dependent shear thinning property. So thixotropic fluids examples are printer ink, enamel. But there are certain fluids for which viscosity of fluids increases with stress. So viscosity of fluid increases with stress over time. In thixotropic fluids, the viscosity of fluids decreases with time. So such fluids are known as rheoplastic fluids. Rheoplastic fluids. So the examples of rheoplastic fluids are bentonite solution, gypsum solution in water, etc. Gypsum solution in water, etc. So rheology basically means is a branch of science which deals with the flow and behavior of polymeric fluids. So rheology is the branch of science which deals with flow and behavior of polymeric fluids.